Okay, let's take a look at this one. We are solving polynomial and rational inequalities. And we talked about the way that we approach this is, first of all, setting this to 0. I'm not going to say equal to 0, but having this number be 0. So the first thing we want to do is subtract the 2 over to the other side. We get this statement. Okay, now we haven't done any that look like this, or if this is the first time you've seen this happening. When we have a rational function that has a secondary transformation here on the outside, there's a couple of different approaches to this. We're just going to take one, and that is, when you look at this, it's far easier to find the domain and the range if you have one fraction, right? So in other words, I'm going to want to put this into this fraction. But in order to do that, it's combining something that's not a fraction with something that is. So I want this to be a fraction, first and foremost. Now in order to subtract these, I need a common denominator. And we've talked about how the fastest way to get a common denominator is just to multiply these together. So I could multiply 1 over here, but that's not going to change anything, right? But I do want to multiply over here by x plus 2. Okay? So our statement now would be x over x plus 2 minus 2 times x plus 2 over x plus 2. Okay? So we're here. Now I'm going to combine these into one fraction. Now be careful, because when we do this, we're subtracting this numerator. I can distribute this 2 into here, but I am subtracting both of those terms. So when I go to write this as one fraction over x plus 2, I've got x, it's going to be minus 2x minus the 4 that I get here. And that's less than or equal to 0. Okay. So the goal here, if we're solving this inequality, is where is this graph? You can look at it this way. Where is this graph underneath the x-axis? Where are the values of this less than 0? Those are the values that are below the x-axis. Okay? What will help us in understanding where that happens is any sort of critical characteristic of this. Are there any vertical asymptotes? What are the zeros? Horizontal asymptotes, possibly. So we want to investigate that with this rational function. If you combine what you have here in the numerator, you end up with negative x minus 4 on the top. On the bottom, we have x plus 2. So we've simplified this statement into this statement. Okay? And like we said, we want to identify the zeros, and we want to identify the vertical asymptotes of this graph. That's where we see, along the asymptotes, we see the behavior that shoots up, right, which could go past 0, or it could shoot down and be underneath 0, underneath the x-axis. Okay? But we also need to know what the zeros are. The zeros of the function come from the numerator, right? So we take the numerator, we set the numerator equal to 0, add 4 to the other side, multiply or divide by negative 1, we get x equals negative 4. So this is an x-intercept of my graph. The denominator determines our vertical asymptotes. So if we set this not equal to 0, we are not allowed to let x equal negative 2, right? Therefore, we have a vertical asymptote at x equals 2. It's not a hole in the graph. If we've talked about rational expressions or rational functions, we know that if this could cancel with something in the numerator, that would be a hole, but it's not. It's a vertical asymptote because this doesn't cancel with what's up here. All right, so we have the two critical values that are going to separate the domain of this function into those intervals that we're going to test with the inequality. Okay? So, I could draw a quick sketch of this, I suppose, while I'm at it, might as well. Okay? Here's what we know. We've got a vertical asymptote at 2. We'll put that over here. We've got an x-intercept at negative 4, which we'll put over here. Horizontal asymptote, we're looking at the degrees of the numerator and denominator. They're both 1. So the horizontal asymptote is the ratio of leading coefficients. So that's 1 and that's 1. So we have y equals negative 1 over 1. So we have a horizontal asymptote here at negative 1. So the graph of this function is going to do something like this. Okay, we've got that, and then we're probably also going to get something like this over here, right? And you can plot those points if you want. This is just for the sake of something to look at. So that's what we expect to see. But what we want to know are where are the zeros and where are the asymptotes, because the asymptote shoots this graph down or possibly up in certain places, or possibly up together in some instances. We haven't seen any of those yet. But the bottom line is we're now taking the domain and we're separating it into the intervals where we stop each interval at either a 0 or an asymptote, and then we pick up on the other side. So the first number that I get to that determines one of these intervals is -4. Then I pick up at -4 and I go until I get to the next value, which is either a 0 or an asymptote, in this case the vertical asymptote at 2. Then I pick up at 2 and go until I get to another point, which I don't have any other points. No more zeros, no more asymptotes, so these are the only 3 intervals that I'm going to look at. And then I'm going to test values in each one of these, okay? Because any point that falls within this interval is either above or below the x-axis, right? So we pick a number, pick any number you want. You could pick -5, you could pick -10, but what I choose is -1,000, okay? -1 billion, whatever you want. If you put -1 billion into this function, let's rewrite it. We've got -x minus 4 over x plus 2. This is what we're trying to, x plus 2. Ooh, wait a minute. My bad. Scratch that. That's supposed to be -2. My bad. Doesn't really change what we're doing. The graph looks a little different, but we're okay with this for right now. Okay, it should have been -2 and not +2. My fault. Vertical asymptote at -2. But we still get to -4 first, then from -4 to -2, then from -2 to infinity. So we're okay. We're testing these values. We plug in -1,000. If you put -1,000 here, that term, -1,000 is going to be positive. If I put -1,000 down here, that value is going to be negative. So I have a positive number over a negative number. The value of that overall, when a negative over a positive, is negative, which is less than 0. So if I plug -1,000 in here, I do get a number that's less than 0. Okay, yes. Pick a number that falls in here. -3. If I plug -3 in here, you can scratch the math out real quick. If I plug -3 in here, that's the opposite of -3 minus 4 over -3 plus 2. What do we get? +3 minus 4, which is -1. -3 plus 2, which is -1. What's a negative over a negative? Positive, right? Is that less than or equal to 0? No. 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 We're not going to include that interval. Let's go over here. Pick a number that falls in here. How about 0? 0 is an easy number to work with, right? Okay, I would say in most cases, I'd say like try a million, because a million gives us values here that are easy to see whether they're positive or negative. If we plug in 0, cover up your x's, because you're plugging 0 in place of these two x's. Cover them up. You have -4 over 2. That's negative over a positive, which is negative. So this is less than 0. So we are including both of these intervals in our values that are less than 0. Now, when we go to write them, we've got -infinity to -4. We've got -2 to positive infinity. Here's where we want to look. First of all, infinity never gets brackets. But we have to determine if we're going to use brackets at -4 and or -2. That's where the graph kind of helps us. My graph's a little screwed up, right? This asymptote is supposed to be at -2, not +2 over here, right? Okay. But what's happening with this graph, once it crosses, it shoots straight up. It's never going to touch -2, okay? It's never going to touch -2. So I have to use a parenthesis every time we have a vertical asymptote in our interval. Every time you have a vertical asymptote, we use a parenthesis. The 0, do we include the 0 or not, is determined by that line underneath. am I allowed to let this function equal 0? In this case, the answer is yes. So since I can include 0, negative 4 was the 0 of this function right here. X equals negative 4, that's the 0. I'm going to use a bracket. So again, we use the bracket because of this. If that wasn't there, I'd use a parenthesis. We use a parenthesis here because it's a vertical asymptote. Okay? Sorry about that screw up on the graph. Didn't really screw us up that much. As long as you understand that our intervals are set up by zeros and asymptotes, and then we're testing values within each one to see if the values make this inequality true or not. We keep the intervals that make that inequality true, we discard the ones that don't.